Okay, so next two things we're going to cover are structures and type classes, and they are closely related. Type classes are a kind of structure. So what do I mean by structure? I just mean a record, as they are also called in some programming languages. So I mean, you know, a bunch of fields together that are aggregated. So here you have a very simple structure. It's the RGB one, and it has three fields which are called red, green, and blue, and they're all of type NAT. So maybe this is to store a color on the computer. So I could also write the fields, you know, one per line. So I could write red on its own line, I can write green, and I can write blue. And you know, a structure is basically just an inductive type that has a single constructor and it has a certain number of arguments, like 3 here. This is a structure. But the structure gives us names for the various fields, and it gives a nice syntax for accessing them and updating them and so on. So we'll tend to use them when we can, when we have only a single constructor that is not recursive, like here for RGB. We'll just go back to what we had. And here are some of the functions that are provided. So you have the constructor make, which takes 3 natural numbers and returns an RGB. And then you have 3 selectors. So you can extract the red component, the green component, the blue component, right, of an RGB value. Okay, and you know, this would be the equivalent code if we did it with an inductive structure, right? So we'd have to define all these functions explicitly, which we don't have to do above. So what we achieve here in 2 lines is what we need, I don't know how many lines here, something like 10 lines to achieve. And this is a relatively small structure, right? So that's why we use them. This is all in a namespace, so we can, you know, forget about it when it's over. Structure also have inheritance. So this structure here is called RGBA because it has an alpha channel in addition to red, green, blue. So we say extends, and then we mention the previous structure, and then we can add fields, right? We could also add beta here, and you know, maybe it's of a different type, and so on, right? And then if we print it, then we see, oh, it created two functions for us. One is a conversion function that extracts the RGB part, and the other one is the alpha component. So it's kind of a record or structure with 2 fields, and one of the fields is recursively a structure itself. All right. So this is a value of type RGB, and here you see the syntax, right? So it has these curly braces. You have to name the arguments, so it's not positional. You can, you know, you can change the order if you want green to be first. Lean will not care, right? You can, well, here's another example with RGBA, where I'm saying, well, alpha, make it that value, right? Hexadecimal 7F. And everything else is stolen from pure red, which I had just above. So dot dot is a syntax that says, please steal everything that is not explicitly mentioned here from over there. So I could say, well, I don't want 0 for green, I want 3F. And then I would only steal the red and the blue. Okay. And yeah, I can print those values, right? So we see this is what we defined, right? We can also define functions, of course. So this is a function called shuffle from RGB to RGB, and you see it sets a red to be green, green to be blue, and blue to be red. So it shuffles the 3 fields like this. And of course, a very interesting lemma we can prove, well, the only interesting lemma we can prove about shuffle is that shuffling 3 times amounts to doing nothing, right? And let's look at the proof. Let's pop up the window, move it to where it should have been in the first place, if you ask me. Maybe make this window a bit smaller. Yeah. So okay, let's see, we have shuffle, shuffle, shuffle of C. How do we prove anything about that? Well, we have to expand the C because shuffle, well, actually, I'm not sure. Let's see, what happens if we just do refill? That doesn't work, okay. So shuffle takes a color, but you see it tries to extract the green component of C and the blue component of C and so on. So if only we expanded the C so that this component would be visible, then things would be on our going our way. So let's look here. So I say cases prime, which is just like induction prime, except that there's no induction hypothesis. Let's try induction prime just to see. Induction prime does the same. Because here there is no induction hypothesis, there is no recursion in the type, so the two are equivalent, but I'm going to use cases when I don't need induction hypothesis or when they are not, because that's what mathematicians would do. They would say by cases, not by induction, right? And that is just misleading if you use a too powerful tactic for nothing. But of course, it's okay. If you use induction, I'm not going to subtract points as usual. If your solution is correct, your solution is correct. Okay, so what we see now is there was an expansion that happened. So the C here, we said, okay, what are the possible cases? And there's only one possible case. It's a case where we have an RGB value. There's there's only one constructor if we see it as an inductive type, right? So there's only one case. And that case is the case where you see C has been replaced by that value. Oops, sorry, that value. So a value, that where red is called RED and green is called green. So it's very mnemotechnic, right? So on the left is the name of the field. On the right is the name of the variable that are there. And of course, the variables were created automatically by cases based on the names of the field. So that's why we end up with this kind of tautological naming, right? But you see, these are really variables in the context. So at this point, what do we do? Well, it turns out we don't need to do anything. Refl can take over from there, because this is, shuffle will extract itself the green component and will simplify, it will, extracting the green from this will return green, and then this will, be propagated to next shuffle, and at the end you'll end up with that value again. So refl can do it. Maybe simp can do it as well, but then we need to pass the definition of shuffle, right? So very often I write simp and then I realize afterwards, I didn't need simp. I could have done it with refl. So it's not always automatic. It's quite common that, oh, hello there. It's quite common that we use too powerful methods, and it's not the end of the world either. So for people who prefer a structured approach, well, you can actually use match to do pattern matching. So to do cases. So you say match C with, and then you have the different cases, the different constructors, and here there's only one. So you say, and here I use shorter names like R, G, and B. And then here I use ecrefl, but I could also write by refl if I want to mix the two styles. Doesn't matter. So this style we're not going to use. I'm just, you're allowed to use it, of course, but I'm just showing it because I want to show the symmetry between structured proof and the tactical proof. Okay, so that was for structures. Structures are really, there's not much to say about them. It's just syntax almost for, concepts we already know. But they're going to pop up in various lectures, even if they're not so interesting per se. So it's good to cover them. So now type classes are quite an important topic in Lean. We're not going to need them much because, again, it's a very bureaucratic concept, and I like to focus more on more essential concepts of interactive term improving, not on red tape. But nonetheless, I mean, type classes have an important role to play when you start using Lean in the wilds, especially for mathematical libraries. So, so if you know Haskell, then you probably know of type classes. It's this idea that you can you can basically bundle various types that have similar properties or the same properties together in a class. For example, all the types that can be serialized to strings, you know, all the types that have a function called toString, you can call it, I don't know, a printable or serializable, and you know, that will be the type class. It will be you know, the set in some sense of all types that have that function or that meet this and that property. So it's a very intuitive concept, because afterwards we can prove lemmas that range over all types that belong to a class. We say, well, if you have that function and if you have that function, then you can do such and such. So in mathematics, it's very useful for things like you know, algebraic structures. So groups, semi-groups, rings, fields, all these things are going to be type classes, right? Because you have several different types that qualify as groups or as ring and so on. So in lecture 12, we're going to cover that in the math part of the course. Until then, we're not going to use type classes much, but it's nonetheless the appropriate point to introduce them, because they're so intimately tied to structures. So the idea of a type class in Lean, it's a bit different from Haskell. It's more general in a way. And if you don't know Haskell, it doesn't matter. I'm not assuming that you know Haskell. I'm just saying, don't be confused if you know Haskell, because it's different. Essentially, type classes in Lean are a mechanism, despite the name, it's a general mechanism for providing default arguments to functions. And typically, these default arguments are types, but not always. And it's a different mechanism from you know, the curly braces that we used before. It's a mechanism that will do a kind of systematic search based on some tables that we're going to fill with information, and that also already pre-filled to some extent with some information. So let's look at a concrete example. So Lean has a type class called inhabited for all the types that have, you know, at least one value. Because in Lean, you can also have empty types, right? So empty types would not be inhabited. The inhabited class, you see, is declared as having one field, which is called default. You see it has a syntax: class, inhabited, such and such. You can read this as structure. It's really the same as structure. It's the same syntax. It's just that it's registered as a class, and we'll use a slightly different syntax ourselves for classes, I think. Actually, we don't even define classes here. It doesn't matter. So there's we can also use an attribute. So we can write, so we can write something like class structure, and that is exactly the same as just writing class and like this. Again, the output of Lean is sometimes more complicated or different than what we enter. We should just not be too confused or worry too much if things look cryptic. I cannot control the output. I can control the Hitchhiker's Guide and everything else, but not the output of the system. So inhabited has one field, which is default, and default returns a you know, an alpha. So we're going to register natural numbers and inhabited. So we just create, you know, a value of type inhabited n. So it's a record, it's a structure. We give it a name, that's a fairly natural name here. And we give it a value, we say 0. And we registered it as an instance. So that means we add this information to the global table. So if somebody ever needs, you know, an object of that type, then the table will say, just use this one here because it was registered. Okay. And the same thing here for list. List is inhabited. No matter what the alpha is, we can return the empty list. And then we see when we eval default of n, we get the default value for n, which is 0, right? If we had set 7, we would have gotten 7. If we remove this attribute, we get 0 because that's a default. You know, this is already registered in Lean. We're just registering it a second time as inhabited, right? And same thing for the list. Now, suppose we want to write a function that you know, returns the head of a list. And the problem is, I mean, I'm going to remove a bit of things here, right? So in the cons case, then that's very easy, the case where there's a cons constructor here. So there's a head, we just return the head. But in the empty list case, we don't know what to return, right? It's like, wouldn't it be nice if we could, out of thin air, create a value of type alpha? The trouble is not all types are inhabited, so we cannot out of thin air do that. But maybe we can at least for those types that we know are inhabited. So this is what we'll do. So we'll say inhabited, default, and then we'll say alpha here. Now Lean is complaining, right? Because it says, okay, failed to synthesize type class instance for, basically what it's saying is like its lookup failed, right? So here, when we ask default for n, it succeeded, default for list of z, it succeeded, but when we ask for default of alpha, it failed. There's no entry in the table for such a general type, nor can there be, because not, you know, all types alpha are inhabited. So how do we solve that? Well, we just push the problem onto the caller of the function head. So we're going to require that alpha is inhabited, and then we're not going to have the problem. So we're going to take an instance, right, an argument here, inhabited of type alpha. And now it's fine, except that we can do better than this, because now the function head will require us explicitly to pass, you know, an argument of type inf, which of type inhabited alpha, which we don't want, right? So if we look at the signature of head, it requires the first argument to be that, and we don't want to ever have to explicitly pass type classes around. The whole point is we register them in some global tables, and everything gets sorted out for us, right? So what we're going to do is we're going to use some new syntax, which is a square bracket, and that means this is an implicit argument, just like with curly braces. But it's going to be resolved using these global tables that I'm talking about all the time. And also you notice I've removed the name because we just don't use it. Lean resolves it automatically. So default takes an implicit argument, you see it's called C, and you know, it just threads things through automatically. It sees, oh, I need something of this type, and then it looks at the context, is there something of that type? And if yes, it just uses it. So it uses a variant of the you know, the algorithm from section 1.1.4 for inhabiting types, you know, based on its global tables, basically, right? And then we can prove lemmas, and also this lemma here requires inhabited alpha, because otherwise we cannot call head. Head requires an implicit argument, you know, of type inhabited alpha. So we have the same issue with the lemma as with the definition. We have to have such a parameter here, and then we can do the proof here. All right, and here again, this is a proof by cases. I could have used induction, but you see there's no recursion. We never look at the tail, so I can do it by cases. All right. This is yet another example, right? So now it returns 7, not 0, because I've changed the definition. But you see, I can call the function head on the empty list, and it returns 0 as expected, or 7, whichever is expected. And you see, yeah, this is the this is the official list head from the library. So what we've just defined actually exists already, and it works in the same way. I can click on it and see it. You see it also requires inhabited and also uses default. Right? And here are some more examples. You can register functions as being inhabited, but this is only conditional on the codomains being inhabited itself, and so on. There are more examples. They're described, I think, in the Hitchhiker's Guide. So this was all about inhabited, but of course, inhabited is not the only type class. So there are some other basic ones. For example, has zero, just has one field, which is called zero. So you create a new type and you say, my zero is whatever. So for Booleans, you might say zero is false and one is true, right? So you'd say my zero is false or my one is true. So it really depends on the type. And these are called syntactic type classes because they don't require any properties like, I don't know, addition has to be commutative or the inverse of the inverse has to be the original value. So, I mean, just like default was also a very bland type class. And here you see somebody has registered natural numbers, the integers, the real numbers, so that they have one, and that allows us to use the syntactic sugar 1 for the constant 1. And in fact, we have encountered type classes in lecture 2, because then we registered the operation add, I think, that we had defined as commutative and associative so that CC would know about it. And so back then, the syntax was just black magic. We didn't look at it. But if you go back at that lecture, you'll see that the syntax makes a lot of sense now that we've covered the material.